So, this is a typical situation in your seat allocation in JEE. Okay. So, it says if the seat allocation is over, then no seat falls vacant, provided that the admission fee is reasonable. Now, the second premise says if the seat allocation is over, then the admission fee is reasonable, and our conclusion is coming after. Therefore, it says if the seat allocation is over, then no seat falls vacant. Now, how do we go around proving that the argument is correct, or telling that, or finding out that argument is incorrect? Right? So, in general, what we do is think of a world where all the premises are true. Then in such a world, the conclusion must hold true. So, this is about all worlds wherever the premises are true. You have to consider now all such worlds. Okay. So, in terms of our interpretations of propositions, what we find is you think of all those interpretations where the premises are true, they are assigned to be 1, right, all the models of the premises, and you see each of these interpretation is such that it satisfies all the premises at a time. Okay. So, you need to consider here that the set of such premises has a model, not only one sentence, one proposition, but a set of propositions now. Okay. So, first we define what we mean by a set to be satisfiable or having a model. So, suppose sigma is a set of propositions So, we say an interpretation I is said to be a model of sigma, and we write it as I satisfies sigma as earlier, when what happens, I satisfies x for each x in sigma. Okay. So, it is simultaneous satisfaction of each proposition by the same interpretation. In such a case, when a model exists, we say that sigma is satisfiable. So, we say that sigma is satisfiable if it has a model. So, all this will be definition. Is it okay? So, now when such a scenario comes, when you have a set of premises and there is a conclusion, you need something else, not only satisfaction of this, but you need that such a model of sigma should also be a model of the conclusion, right. So, that we formalize as follows, taking W to be any proposition, it may be in sigma, may not be in sigma. We say that sigma semantically entails W, we write it as sigma entails W if each model of sigma is a model of W. Is it clear? Is it going along with our intuition that imagine a world where all these premises are true? In such a world, the conclusion must hold, right. Our worlds are now only interpretations, fine. So, now if such a thing comes, such an argument comes, how are you going to proceed? We have a formal definition now. So, first thing is you have to write it as an entailment, as a consequence. So, now this says, sometimes we omit this semantically adjective, sigma entails W, but sigma entails W means the argument is correct, that is what we are writing cryptically without introducing what is a consequence, right. So, what we do is we again introduce cryptically the notion of consequence. We say that the consequence sigma entails W is valid, to say that sigma entails W, right. So, the adjective the consequence we will say that we do not know till now whether it is valid or not. Once it is valid we can write this way, right. So, it is overloaded in that sense. So, whenever sigma entails W we also read it as the consequence sigma entails W is valid. Okay. So, there is a philosophical overturn, so that creates problem. So, because we are not defining what a consequence is, we are defining only validity of a consequence. Then to refer that it is a consequence, we just put the adjective the consequence sigma entails W, okay, which means we do not know whether it is valid or not. Once it is valid we can write that as sigma entails W, okay, without the adjective. Now, first thing is given an argument we want to write it as a consequence. So, in that form which is to be validated or to be seen that it is not correct, right. Now, how do we do it? See, mathematicians are basically lazy people, they do not want to take a big expression, they would write a symbol for it, that helps clarifying the concepts. Okay. So, what we do here is first identify the atomic propositions, write them in symbols and then see how we can translate to sigma entails W, fine. So, first thing is we identify that. So, here it is the seat allocation is over 1, second is say no seat false vacant, you can say seat false vacant also, then negate or something, but it does not matter because always it is coming as no seat false vacant, everywhere it is occurring like that. So, we can start from the beginning no seat false vacant. Next, the admission fee is reasonable, that is all. Okay. So, let us write them. Say P stands for the seat allocation is over. Next, Q stands for no seat false vacant. And R stands for the admission fee is reasonable. Okay. So, how do we symbolize the first premise? If P then Q provided that R, provided that means if, that is another if. Okay. So, P implies then this if this, R implies Q, it is Q if R, right. So, if R then Q, fine. So, you may write P implies R implies Q. Sometimes you may write it as R implies P implies Q, right. We will see that they are equivalent. Okay. What is the next premise? What is the next premise? P implies R. That is all about our premises. So, we have the set of premises as this, which is sigma. We want to check whether this entails the conclusion. So, the conclusion is P implies Q. Okay. So, now again we are lazy people, we do not want to write the braces. So, what we do, if it is a finite set, we make it a convention not to write the braces. Okay. So, if that means if sigma is some finite sentences W1 to Wn and we have a consequence of this form, we would write it as W1 comma to Wn entails W. Okay. So, here you can just omit the braces, that is what it says, but that is only a convention just to write less. Now, how to validate it, whether this is valid or not? You have to go for interpretations and see what are the models of this. So, one is you can take the truth table. Okay, let us construct the truth table, then we come to Sutter wise. So, we have here 3 propositional variables, okay, and then 3 sub propositions, R implies Q, P implies R, P implies Q, and another P implies R implies Q. Okay. So, let us take say R implies Q, then P implies R implies Q, next P implies R, next P implies Q. And we construct the interpretations. There will be 8 lines. Okay. These are the 8 interpretations. Now, you have to evaluate all these connectives. So, R implies Q, that becomes 0 only when R is 1, Q is 0. So, this case it will be 0, this case also it is 0, nowhere else. Okay. Next we go for P implies R implies Q. So, that will be 0 when P is 1, R implies Q is 0. So, this case. That is all others are 1. Next we go for P implies R. So, that will be 0 when P is 1, R is 0. All others 1. So, next we go for P implies Q. So, that will be 0 when P is 1, Q is 0. Here is 1, third line, and the last but 1 line. All others are 1. Okay. Now, then what we are required to do? Find out all the models of all the propositions simultaneously, right. So, take one interpretation, take one row which satisfies both the premises at the same time, evaluate it to 1. Okay. So, this must be 1, this must be 1. So, this is one interpretation. Next, this is another interpretation. Fourth one is one more. Sixth one, right, then the eighth one, Is it okay? So, let us number them. We say it is 1, 2, 3, 4, 5, 6, 7, 8. Out of this we have 1, 2, 4, 6 and 8. These are the interpretations which satisfy sigma. Now, you have to check whether all these interpretations also satisfy W, the conclusion, fine. So, we do not have to consider the interpretations which are not satisfying at least one of the propositions in sigma. Is that okay? We do not have to consider them. Now, then in the first interpretation P implies Q is 1, right. In the second interpretation P implies Q is 1. In the fourth interpretation P implies Q is 1. In the sixth interpretation P implies Q is 1. In the eighth interpretation P implies Q is 1. So, the requirement is satisfied, right. So, each of these models of the premises that is in the lines 1, 2, 4, 6 and 8 is a model of conclusion. Hence, the consequence is valid. Is it clear? Now, we can look at it in a different way. Instead of looking at all the models of the premises, we can try to see where the conclusion is falsified, right. In all those cases, the interpretation must falsify at least one of the premises, right. If that is correct, then also sigma entails W. Is it clear? So, that means here I will be considering all those lines which are not starred. So, that is third, fifth and seventh. In the third one P implies Q is 0, okay, and in the seventh one P implies Q is 0. I do not have to consider the sixth one where it is 1. We take only those where P implies Q is falsified, right. Now, what happens? It can come in certain other scenario that the unstarred ones will have a 0 here, right. So, it is not the starred or unstarred, we have to start from wherever P implies Q is 0. It so happens here is that they are within this, that is why sigma entails W, right. In general that may not happen. So, our procedure says we should look for zeros in the column for P implies Q and then try to verify whether in each of those rows wherever P implies Q is evaluated as 0, at least one of the premises is also evaluated to be 0, right. So, we start from third line, there P implies Q is 0, we find that one of these premises P implies R implies Q is 0. Next, in the sixth line we find P implies Q is 0 and one of the premises P implies 0, P implies R is evaluated 0, therefore sigma entails W. Is it clear? So, that can be going as an alternate definition to this, in fact that follows from the definition. It says if I falsifies W, then I falsifies at least one of the premises in sigma, then you say sigma entails W. Is that clear? Okay. Now, from the definition you can see easily that if sigma is unsatisfiable, what will happen to sigma entails W? If sigma is unsatisfiable, yes, for which W? Any W?
Yeah.
Is it clear? What is the reason?
Sigma itself does not have a model, so
Okay.
it is always going to be, if you can look at it as the first few propositions implying what we want. So if all the propositions together itself is never satisfied,
Okay.
so it's like 0 implying.
Not like, give the argument correctly.
Any model of sigma is a model of W.
That's what we want to verify. Okay.
Sigma has
Now sigma has no model. So vacuously, every model. Okay. Is that clear? You see it in a different way, it will be easier to do. The other alternative way. You say, when is sigma does not entail W? If you find one model, find one interpretation, or there exists one interpretation which is a model of all the propositions in sigma, but not a model of W, right? But you can't find any because there is none. Is it clear? So that is an easier way of looking at it. So let us write it down. So it says, if sigma is unsatisfiable, then sigma entails W for each proposition W. Well, so what is the proposition? What do you want to propose or suggest?
Then empty set entails W if W is valid.
Is that okay? And what is the reason? Well, let us carry the suggestion up and see what is happening. He suggests that it should happen this way. So, what is the model of an empty set? I would claim that every interpretation is a model, right? Is it okay? Otherwise, you have to find one interpretation which is not a model of one of the propositions in empty set, but there is none. Is it clear? We can't find a non model of some proposition in empty set, because empty set has no proposition in it. Therefore, every interpretation is a model of it. So, any interpretation satisfies the empty set. Fine. So, if this is given that empty set entails W, then any interpretation is also a model of W. Therefore, it is valid. Right. Conversely, if every interpretation is a model of W, then every such interpretation is also a model of empty set, or you start from any interpretation which is a model of empty set, right. Now, that happens to be a model of W because W is valid, therefore, empty set entails W. Is that clear? In fact, once W is valid, every set will entail W. Is that right? So, you may write this way. If W is valid, then sigma entails W for each set of propositions sigma. Is it okay? So, one of this is the empty set for the converse of that. Fine. This shows why valid propositions are really redundant. They have no information content, because it can be conclusion of any set of propositions. Okay? But we will see it in a different way now. Let us say X is a proposition in sigma, okay, it is given, and X is valid, and also sigma entails Y. then we may say sigma minus x also entails y. It shows the redundancy, that any valid proposition from the set of premises can be deleted. The same conclusion you will get as earlier. Can you see how does it happen? Okay, let us see what is to be done. We are given with x is a member of sigma, x is valid and sigma entails y. Anywhere we can use them. Now, suppose you want to prove this, sigma minus x entails y. Then how to prove this? You have to start with an interpretation which is a model of sigma minus x. So, suppose you start with that, let I satisfy sigma minus x. Remember, our aim is to show that sigma minus x entails y, that is I should be a model of y, that is what we want. Okay. Now, look at this I is a model of sigma minus x, but x is valid. So, I is also a model of x. Is that okay? Once x is valid, any interpretation is its model. Here is one interpretation I, that has to be a model of x. Now, I is a model of sigma minus x, I is a model of x. So, I is a model of sigma, right. Okay. Now, you use this hypothesis, but sigma entails y. Sigma entails y means every model of sigma is a model of y. So, I is a model of y, and there we stop. That is what we wanted to show. Every interpretation that is a model of sigma minus x is also a model of y. See, what I propose is this. I take u entails v if u implies v is valid. This is the reason we want to be getting interested in validity, though they are redundant, because these entailments can be seen as also valid propositions. Of course, not the same proposition, it is a different proposition, but it can be reduced to checking for validity. Fine. Now, how do we prove this? Suppose we start from this side. Suppose u entails v. We want to show that u implies v is valid. Right. So, to show that u implies v is valid, we have to verify taking any interpretation that it is a model of u implies v. Right. So, let I be an interpretation we want to show that I is a model of u implies v. Okay. Now, you have to exploit u entails v, right, but u entails v says if something is a model of u, then only it will be a model of v. So, there will be another case where it is not a model of u. So, we break into two cases now, right. So, case 1 A is I is a model of u, and case B is when I is not a model of u, right. Now, in case A, if I is a model of u, utilize the fact that I entails v, therefore, I is a model of v, right. So, this gives I is a model of v. If I is a model of v, then I is a model of u implies v, because u implies v is true when v is true, right. So, this case says I entails u implies v. In this case, if I does not entail, does not satisfy u, right, then by definition of implies I satisfies u implies v. If I of u equal to 0, then I of u implies v is 1, right, whatever V. So, in this case we directly get I is a model of U implies V. Okay. And that is only one part. If U entails V, then U implies V is valid. What about the converse? It should be easier, because this breaks into two cases, that should give only one case. Okay. So, conversely, suppose you have to start with a model of U, and so that it is a model of V. So, using U implies V is valid. Suppose U implies V is valid, let I be a model of U. Our aim is to show I is a model of V. Okay. Now, I of U is 1, I of U implies V is 1, therefore, I of V is 1, nothing to do. Is that okay? That comes from the definition of implication. Okay. It can never be 0, right, or you can go the other way. If I of V equal to 0, then what happens? Then I of U implies V equal to 0, right. This contradicts the validity of U implies V. So, I is a model of V. Once you see there is a connection between entailment and the connective implication, validity of that, then you can connect equivalence with validity, right, because U is equivalent to V means U if and only V is valid, right, and U if and only V can be broken down into two parts, U implies V and V implies U, right. So, you may say that U is equivalent to V if and only if U biconditional V is valid, if and only if U entails V and V entails U. U is valid if and only if U is equivalent to top, yeah, if and only if top entails U. Now, you are giving only one side, U entails top always, whatever U may be, right. So, only this part is relevant here in this. This is also clear. Once you say U is valid, it means every interpretation evaluates U to 1. So, take any interpretation, you want to show U is equivalent to top, but what is top? Every interpretation also evaluates that to 1, fine. So, under any interpretation U and top are interpreted the same way, are evaluated 1. So, they are equivalent, fine, and conversely. Then you can do for unsatisfiable, U is unsatisfiable if and only if U is equivalent to bottom, okay. And again as earlier we can take only one part. So, this says U entails bottom. So, let us write that again. V is valid, then U entails V for each V, each proposition U. and if you say V is unsatisfiable, then V entails U or is U. So, now you can utilize all your interpretations and models for finding out various tautologies or valid sentences or even valid consequences. Okay. For example, you have the idempotency, you take x any proposition or with x itself you would get x, right. So, these will help you in calculation when you calculate or compute something, how is it going to be valid or not, to check it. These types of equivalences will be helpful. So, let us mention some of them. So, this law says you take any propositions idempotency says x or x is equivalent to x, x and x is equivalent to x. Okay, it is clear. Similarly, you have De Morgan, which says not of x or y is equivalent to not x and not y, and not of x and y is equivalent to not x or not y. They are easy to prove from the truth tables. You have commutativity, which says x or y is equivalent to y or x, x and y equivalent to y and x. Okay. X biconditional y equivalent to y biconditional x, right. Similarly, distributivity, there are so many distribution laws, we will give only one or two. So, this says x or y and z is equivalent to x or y and x or z. Okay. In such case, you say or distributes over and, like your multiplication distributes over addition or distributes over and. Similarly, and also distributes over or, unlike the arithmetic. So, we say x and y or z is equivalent to x and y or x and z. Even implication distributes over itself. Yesterday we have seen x implies y implies z will be equivalent to x implies y implies x implies z. Okay. So, there are so many other distribution laws. Something called hypothesis invariance. It says x implies y implies x is valid. Okay. And that distribution of implication also you can take as one of the laws. Next we check say law of contradiction, which says x and not x is unsatisfiable. Right. And there is one more which does not look like, but we will say why it is called contradiction. It says not x implies y implies not x implies not y implies x. This is valid. if you read this implies as your entailment, once it is valid you can see that entailment. So, it says assuming not x, if you derive y, and assuming the same not x, if you derive not y, then x must be correct one, not x is unsatisfiable, x is valid, right, then x must be true. That is why it is also called law of contradiction. Intuitively it means that assuming not x you get y, assuming not x you get not y, therefore, assuming not x you have got a contradiction, therefore, not x is incorrect, x must follow, right. So, that is why. Okay. There is something called modus ponens, this is very helpful. It says x implies y, from that you can conclude y as a consequence. Once you write it as an equivalence, you can also keep your x. So, that means x and x implies y is equivalent to x and y, right. In this consequence you are not showing x, but x is still there once you assume this, therefore, you can write it is equivalent to x and y. Okay. Then there is something called contraposition, which says not x implies not y is equivalent to y implies x.